In this video, we are going to look at the relationship of the ideal gas law and why it's an important addition to our arsenal of other gas laws. One thing that the ideal gas law allows for us to do is to introduce a new variable, and that new variable is n, and it's usually written with a slight italicized, almost cursive n. And what that does is it represents the number of moles. So now we can actually start talking about the amount of a gas and how the amount of a gas is going to change all of our gas law that we've gone over so far. So first you have to think about, well, what would the amount do to our combined gas law equation? So in combined gas law, we have PV over T. So the more volume that you add, the more gas you have. So if it is directly proportional to the volume, we're going to put the amount in the denominator so that when the volume increases, so does the amount, and vice versa. When the amount increases, so does the volume. With the combined gas law's addition of the amount of a gas, we now don't have to worry about this before, after initial, final business with all of our readings. So with that, we are basically going to allow for scientists to determine how much volume or pressure or how many moles of gas or what the temperature would be if you can't read one of those four. And we do that by actually plugging in what we already know about a gas, ideally at STP. All right, so bad corny joke, but ideally, what do we already know about gases? So we already know that at standard temperature and pressure at STP, if we look at this PV over NT proportion, we have 1 atmosphere of gas. That's going to be the easiest unit because it has the value of 1 mole of gas, again, also the easiest number to plug in, is going to occupy 22.4 liters and be at 273 Kelvin. So if you take and plug into your calculator, go grab your calculators, okay, plug in 1 times 22.4 divided by 1 divided by 273, and you're going to see this value come up. Okay, you are going to see 0.0821. Actually, you're going to see 0.06, but we're going to round it to 3 sig figs. And we are going to then call PV over NT the gas law constant R. Okay, this constant is going to have real units that we need to pay really close attention to. The units are going to be liters times atmospheres over moles times Kelvin. So I always call it latums per molk. All right, liter atmospheres, mole Kelvin. It's molk, not milk. But with that, you can end up actually making sure that we have everything canceled out correctly. So when you plug in what you know to the combined gas law, you can see how we actually are going to derive the ideal gas law. Okay, so here is the original combined gas law. P1V1 over T1 equals P2V2 over T2. We then add in N, okay, for our amount. Typically, gases don't escape. All right, they are basically going to stay exactly the way that they are in their sealed container. On this right-hand side, we plug in everything that we know. Okay, here's our gas law constant R. That's going to represent this side. This is what we get in our calculator, which is then rounded to 0.0821 as our value with 3 sig figs. And we get PV over NT equals R. That is not a user-friendly version of this, so we are going to take our N and T and multiply them on both sides so that we end up bringing the N and T over here. So we get PV equals nRT. PivNert is our expression for the ideal gas law. It is how it is affectionately referred to by most people. PivNert, please don't say pervert. PivNert and PV equals nRT. Okay, but really important to remember is that if you are using PV equals nRT and our gas law constant of 0.0821 liter atmospheres per mole Kelvin, you must be in liters. You have to be in atmospheres. You have to be in moles, not grams, and obviously Kelvin. So if you use a different unit, you have to use a different gas law constant for R. And it's derived the exact same way. This one's in your millimeters of mercury, this one's in your kPa, but typically AP students use these to save time. You don't have to use them. These are definitely optional. I usually tell my students to stick with the 0.0821 liter atmospheres per mole Kelvin. Okay, so let's see how this is used and how this is used to answer a sample problem. So here we have a question that says, how many moles of oxygen will occupy a volume of 6.2 liters at 9.8 atmospheres of pressure and 25 degrees Celsius? Okay, so again, if you ever see moles, you're going to see that we are going to use that constant variable n, or n, not a constant variable. Liters is going to be our volume, atmospheres is going to be our pressure, and obviously we have our degrees Celsius as our temperature. So we can write P is equal to 9.8 atmospheres. V is going to be our 6.2 liters. N is unknown. R is a constant, 0.0821 liter atmospheres per mole Kelvin, and temperature is 25 degrees Celsius. So before we plug in anything, we have to make sure that we are in liters, atmospheres, moles, which our answer will be, and then Kelvin. So we have to change our 25 Celsius, add 273, get 298 Kelvin. So now that all of our variables are in the correct units, now we can plug into PivNert, PV equals nRT. All right, again, since we are looking for n, I like to isolate the variables first before we plug in so that it's less writing and it's less confusion. So how do I get n by itself? Okay, it's being multiplied by R and T, so I'm going to divide by R and T. If I divide one side by R and T, I also have to divide the other side by R and T. So I get N equals PV over RT. That is the equation that I am going to plug into. So I'm just going to rewrite it the other way. N equals, and now I'm going to plug in my PV over RT on this side. So my pressure is 9.8 atmospheres. My volume is 6.2 liters. R is 0.0821 atoms per mole. And my temperature is 298 Kelvin. Okay, so in the calculator, what do? You multiply everything in the numerator and divide by the denominator. Denominator means divide. So in my calculator, I put 9.8 times 6.2 divided by 0.0821 divided by 298. You only have to plug in once. You don't have to then put something else in there. All right, and we get 2.50. Now, what are my units? Okay, N is moles. Okay, so everything but moles should cancel out, but does it really? All right, atmospheres will cancel out with atmospheres in the numerator over here. Liters will cancel out with liters. Kelvin will cancel out with Kelvin in the denominator here, resulting in 1 over 1 over moles. So basically, the inverse of inverse moles. So what is that going to be? That's going to be the unit of moles. Voila, we have our units all work out. So what you'll see next is the exact same notes that I have for my students. In their slides, they have their pressure, volume, their N identified in case they can't read my handwriting while we're doing these in class. And then we have our PV equals nRT, and you see we have our 2.5 moles. And that is the ideal gas law.